In this video, we're going to start exploring the equations of sinusoidal functions. The sinusoidal equation has the form y equals a sine b times x minus c plus d, or if we're looking at the cosine function, it's the same thing but with the cosine there instead. In this lesson, we'll learn how the values of a, b, c, and d affect the shape and location of the graph of a sinusoidal function. These values are called parameters of an equation. Note that the equation y equals sine x could be written as, so what we're looking at is we're going to replace a, b, c, and d with values so that it would be equivalent to that. And if that's the case, your a value is 1, your b value is 1, your c value is 0, and your d value is 0. And that would give us the same parent function that we've been looking at and comparing to. Okay? So they're saying, okay, graph the following on your TI. Now, I've actually used Desmos just because it's a little bit clearer and easier to see on Desmos when we're doing an exploration like this. And then we'll see how we can do this in our graphing calculators. So if we look at Desmos for a second, I just put in y equals sine x as our first function, and we can see that graph. Okay? Now, if I turn on the next one, y equals 3 sine x, and you compare, I'm going to make this so I can fit the window in, right? You can see what happens. Move this over. Right? You can see what happens to our graph. Right? The red one is our sine function, and we're used to, if I stretch this out, right? If I go from negative 360 to 360, or in this case, negative pi to pi radians, right? Look what happens when we put that 3 in there. Our maximum and minimum are no longer 1 and negative 1. I can't even see it on my screen, so I have to scrunch it all up and see that it goes from negative 3 to 3. Okay, so let's turn on another function. If I turn on negative 4 sine x, what does that do to my graph? If I turn the other one off, we're just going to compare back to the sine x parent function. Okay, so my parent function, my minimum value is negative 1, my maximum value here is positive 1. Now, not only is my minimum value negative 4 and my maximum value is positive 4, but my whole graph somehow flipped upside down. Okay, now let's take a look at the 1/2 sine x compared. Okay, well, it's right side up, but my minimum value is negative 1/2 and my maximum value is positive 1/2. So in terms of where my graph is going through those key points, that stays the same in terms of my x-intercepts. My x-intercepts, if I turn them all on, you can see the x-intercepts are exactly the same for all three of them. But what has changed are my amplitudes. And then when I put a negative in there, it actually flipped my whole graph upside down as well. So what I've done here on Desmos is I've actually tapped on all my x-intercepts, so you can see the x-intercepts for all 4 of those graphs are the same, and then I've also tapped on the maximum and minimum points. So for the first curve, you can see my original graph, which is the red one here, right? My maximum's at 1. Then the second one we did was the blue one. No, sorry, the second one we did was the blue one. And at pi by 2, or 90 degrees, my maximum's 3. For the third graph, which was negative 4, the green one here, if we go down, you can see at pi by 2, the first point that it went to was negative 4. And then the fourth graph, the orange one here, at pi by 2, or 90 degrees, we were at 0.5. Okay, so let's go back to the notes here. And I've actually just pasted that into my notes so that you can have that there. But you can go ahead and draw that in on your notes as well so that you can see where those key points are. Alright, let's take a look at the next page here. It says, how are these graphs similar? Well, they're similar because we just looked at they all have the same x-intercept, and they also have the same y-intercept. If I go back to the graph here, you can see the x-intercepts we looked at already, and then the y-intercept is actually at 0, 0 as well. So that hasn't changed. Now, if we look at our domain is the same, right? Negative infinity to infinity. We look at our median line, that's our x-axis, so that our median line is at y equals 0. And then our period, we're still going from negative 2 pi to 2 pi. Like you can see here, one cycle for all of them is still from negative 2 pi to 2 pi. So that hasn't changed either. Let's add that to our notes. So our median is y equals 0, or x-axis. Our domain stays the same. And the period's the same. Oops. Now you could do this in degrees or radians, it doesn't matter. It's going to give you the same answers. Now in terms of how they're different, well, we saw that their amplitude changes. And because of that, so does our range. Right? So for our first graph, it goes from negative 1 to 1. For our second graph, it went from negative 3 to 3. Our third graph went from negative 4 to 4. And our fourth graph went from negative 0.5 or 1/2 to 0.5. Right? So the range changed. So because the range changed, the max and min also changed. So is there something we can predict or interpret in terms of our a value? What is the connection between a and the shape of each graph? Well, if we have a look back here, when a value is 1, what was our maximum and minimum? Right? So a value is actually determining our amplitude. So when a is 1, our amplitude was 1. When a was negative 4, our amplitude was negative 4 or 4. Right? So there's the connection. We can also see that when it is negative, right, that's the other question that we're going to be asked, what happens to our graph? Okay, well, let's write down what a value means first of all. So the connection between a is that a changes the amplitude. And this also changes the range, the max, and the min. Alright, so here it says amplitude is sometimes referred to as the vertical stretch. So if you see that coming up, that's what that means, and that's related to our a value. The maximum vertical stretch, or the vertical displacement from the median line at the high and low points, is equal to the value of a. Now here's what I was leading to before. Note positive or negative for a vertical flip, right? So if you have a positive a value for y equals sine of x, you'll get your regular sine function that should look like that, right? And if your a value is positive for cos of x, you'll get your regular cos function that would look like this. But if your a value is negative, that's going to flip over. So instead of going up first, it's going to go down first. You'll have a minimum first and then a maximum. And same for the cosine graph. If it's y equals negative cos x, you'll start at negative 1 instead of positive 1, and it would go like this. Okay? So make sure that you're comfortable and able to use a positive a value and a negative a value, and also know that that a value determines your amplitude. Alright, let's take a look at the b parameter. I find b is a little bit harder to interpret, but let's have a look at that one. So it says here, graph the following. Instead of on our TI, we're going to do that in Desmos and have a look. So let's go ahead and do that. So as you can see on the side here, I've put all 4 of those graphs in, and we're going to look at them each separately. So again, our parent function, y equals sine x, this is what we're used to looking at. Now what happens if we change the coefficient of x inside the sign? So if we look at y equals sine of 1/2 x and turn that one on, what do we see here? So I'm going to just tap here and let's have a look at our amplitude. Well, our max and min haven't changed, right? As compared to our max and min on our graph here, that hasn't changed. But the location of my max and min has changed, right? So for the first curve here, I'm going to get rid of some of these just because it's lots to look at. At 1/2 pi, or at 90 degrees, my maximum was 1, and that's what we're used to for sine x. But when we did 1/2 sine x, you would think it would be half as big, but it actually seems to have moved it over to the right. So instead of at 90 degrees, or pi by 2, I'm now to 180 degrees. So it's actually pushed my amplitude over and made my graph a lot bigger in terms of its stretch. So when we're looking at our b-value, we're looking at our horizontal stretch. So what would happen, so that's when I made my b-value smaller. What happens if I make my b-value bigger? What would you anticipate is going to happen if I change that b-value to 2? So if I do that, so it's actually going to double, right? The amount of curves, right, or amount of cycles in that same amount of space. So if I look here, my first amplitude is going to happen at pi by 4, so quicker than the other one that was at pi by 2. Okay? So we're looking here and we're seeing that our b-value, as it gets bigger, the amount of curves, or the amount of cycles that happen in the same amount of space increases. Okay? Let's take a look at 6. So that was double the amount, right? So if you look at one cycle, I'm going to get rid of the amplitudes here. So I started at 0, 0, and for my original curve, that's sine x, that one cycle is at 2 pi. But when I'm looking at sine of 2x, one cycle is at pi. Okay? So one period is smaller than one period of sine x. So if I go and put the other one back on here and take that one off, that's sine of 1/2 x. This period, you can't even see one full period. If I go here, that would be over here at 4 pi. So one full period for the red curve is 2 pi, and it looks like it takes 2 sine x's, right? I have to fit 2 of them in for my 1/2 x. So that's 4 pi for the period. So if we look at the 6x, look at how many are fitting in there, okay? So one cycle, one cycle for our sine x curve is 2 pi, whereas one cycle here, and I go up again, right here, is pi by 3. Okay, pi by 3. So that's squishing in way more cycles for the same amount of space. So how many cycles actually fit in 2 pi? Well, you can see here, so up, down again. So every pi by 3, so there's another one, and there's another one, and another one, and another one. So there should be, right, 6 of them fitting in there. So if I put all of these graphs on there, you can see how they're all related to one another, right? I could turn these points off so it's a little bit clearer. But you can see how the horizontal stretch changes the period of your graph, right? You can see in just 2 pi what's going on. It gets a bit distracting with everything turned on at the same time. But you can also see where they all meet up again, right? So I've gone back and I've changed the colors of our graphs just so it's a little bit easier to see maybe what's going on in the same amount of space. You can see all those different curves. It's a little bit easier to draw in on your notes there. Alright, let's go and summarize all of this in our notes. Alright, so I've pasted a copy of what we just did into our notes, but you should probably draw a graph of that, draw a copy of that, so that you have that relationship clear for yourself. And I've put those key points in for what the different periods were for each of our 4 graphs. It's also a good idea to label each of the graphs so you know which one is which, right? And you should probably go back and do that with the other one as well. So let's quickly do that before we finish summarizing. We should have done that before. Now we have those labeled, so we have those in our notes. Okay, so let's summarize our b value. So if we looked at our graphs again that we just did, how are these graphs similar? Well, the domain goes from negative infinity to infinity. The range is from negative 1 to 1. We can have a look at that again. Right? The range hasn't changed at all. We're going from negative infinity to infinity, which also means our median line hasn't changed if we're going from negative 1 to 1. Our minimum hasn't changed. Our maximum hasn't changed. Those are all the same for all of our graphs. My y-intercept is still 0. Right? So all of those are the same. So how are these graphs different? Well, the period and the x-intercepts have changed because it is that horizontal stretch. Alright, so our x-intercepts and our period have changed. What is the connection between b and each graph? Well, b affects the period of the graph. We can write that down. So if we look at each of our 4 graphs separately, when we looked at y equals sine x, the period is 2 pi, or 360 degrees. When we looked at y equals sine of 0.5x, the period was then 4 pi, or 720 degrees. For y equals sine of 2x, the period was pi, or 180 degrees. And then for sine of 6x, this would be 2/6 pi, or pi by 3. We can write that instead if you want. And then in degrees, that would have been 60 degrees. So the period of each graph definitely did change. Now, there is a formula we can see down here. It says the period of the graph depends on the value of b. From the examples above, that we see that in each case, the period is 2 pi divided by b, or 360 divided by b. So that's if you're solving for the period. The period of a sinusoidal function, y equals sine of bx, is 2 pi over b, or 360 over b, which is the exact same thing that we just said. So that's the horizontal stretch. So you're squishing of your graph, or you're stretching of your graph, but you're not changing that amplitude. Okay, so let's take a look at C now. C is a phase shift, or a horizontal shift. So it's like we're taking our sinusoidal graph, we're picking it up, and we're shoving it over one way or another. Okay, so let's take a look at this again in our, not in our graphing calculator, but in Desmos. Alright, so for our C value in our notes, it asks us to do this both in radian mode and degree mode. So I'm going to do this in radian mode first. I've just left, on Desmos, they do the x-axis in radians in this way. If you'd rather have it as in pi, right? So like you can see when you tap this point, that's pi, that's 2 pi. So if you'd rather label your axes in terms of pi radians, that sometimes makes more sense than labeling it in terms of radians without the pi's in them. Just make sure that you're comfortable with both, because you're going to see it in various different ways. So here's just our sine graph, okay? So for graph number 2, it says sine of x minus 1.6. So if I turn that one on, what has changed? Well, my median line hasn't changed, my max and min hasn't changed, but my graph has moved over, right? If you compare the red graph with the blue graph, it has definitely moved over. So if we look here, there's that 1.6 that is showing up in the equation. So which direction did our graph move? Did it move to the left or to the right? Well, if you look at the starting point for our red graph, which is our sine graph, it starts at 0. But it doesn't appear that our graph is sitting at that same spot. It looks as if there's a space, if you look here, from the 0 to the 1.6. Our graph has moved to the right, shifted to the right 1.6. Now let's try to turn on another one. If I do minus pi, compared to what we just saw, what do you think might happen? Well, it has the same sign, So we would anticipate it moving in the same direction. Well, there we go. Okay, so our graph, our red graph, our sine graph is at 0, right? And now we've moved over, and our green graph is our new one, and it looks as if it's moved over pi radians. Let's try this last one. It's plus 0.8. So the other two are minus, this one's a plus, so we would anticipate it's going in the opposite direction. And you can see there's that negative 0.8. It has moved over. Okay, so our shift, a horizontal shift, is actually the opposite of what the sign says in our graph, okay, or in our equation. So if I put the equations on here, I'm going to move this over, you can see that 0.8. So if we turn them all on, it's sort of hard to see with all the labels on here. So I just removed the labels and zoomed in here so we can see exactly what's going on for each of our graphs. So the red graph again is our parent function, and then we can see our shifts from our negative ones are actually shifting to the right, and our positive ones a shift to the left. So you can see where those starting points are as compared to our graphs. Okay, so be sure to draw that in on your notes where it says the radians one. So we'll put that in first, and I've already copied and pasted that. Oops, not there. There. Copied and pasted that into my notes. And now we're going to go ahead and do the other one in degree mode, and hopefully we'll see the same behavior. So let's go ahead and do that. Okay, so I've put in our 4 graphs again, and I'm graphing in degree mode, so you'll see that my axes looks a little different. I'm going from negative 360 to 360 here. And let's put in the plus 45 degrees and see how that's going to affect our graph. So we can see our starting point for our sine x is here at 0, 0. And then you can see, because this is a plus 45, we've actually shifted negative 45 here. If you test it up here, that's 135. That's not the 45 that they're talking about there. So the 45 degrees is over here to the left. So it's a shift to the left of 45 degrees. So what does that mean for the 90 then? If a positive means a shift to the left, then this should mean a shift to the right of 90 degrees. Let's see if that's actually true. And test that point. There it is. It is that 90 degrees. So now you can anticipate, taking a look at the C value, you can tell which direction that we had that shift in. Okay? Let's take a look at the last one. So that's sine of x minus 60. So we would predict that would be a shift to the right 60 degrees. And there it is, 60 degrees. So we could put all of those on there, and you can see the shift for each of those graphs. Where's my green one here? 90 degrees. There we go. So we can see that for all of those, nothing has changed except for the left or right shift. All right, let's draw that in our notes and then summarize our findings for both our degrees and our radians, which actually are the same, which was what we had hoped for. All right, so I have those in my notes. I hope you have those in your notes too. Okay, and you can see that I've labeled those phase shifts. So you should probably go ahead and label each of your graphs so that you know which one corresponds to which graph. And it's a little bit easier to see because the phase shift actually is exactly the value that shows up in your equation. So go ahead and label those now. All right, so let's answer the question that we're being asked down here. What effect does C have on each graph? So what do we summarize from everything that we've looked at so far? Well, the graph moves left or right C units, right? So whatever that C value is, we can see right in our graphs, that's where it's moving. But how does it move? Well, it kind of moves opposite of what we anticipate. So if the sign of the phase shift is negative, it's moving to the right. And if the sign of the phase shift is positive, it was actually moving to right in that many spots. So let's write that down. And at the bottom here, it actually summarizes things quite nicely. It says the shapes of the graphs remain the same, but the graph shifted to the left or the right by C radians. The graph shifts in the opposite direction to their sign in the equation. Compared to y equals sine x, the graph of y equals sine of x minus c is shifted horizontally by C radians. the horizontal shift is sometimes called a phase shift. You might want to write in there that if it's minus c or negative c, we're moving to the right. And if it's a positive c value, we're moving to the left. Just as a reminder that it's opposite what you would think looking at the sign. All right, so our last parameter is d. So let's have a look at how d changes our graph. All right, so I chose to do this in degrees just so that it would fit nicer on our graph here. But I've put in our 4 graphs that we want to explore. So what is changing this d value? We've got some are positive, some are negative, some are whole numbers, one of them's a decimal place. So I've got sine sitting here, sine of x. So let's turn on sine of x plus 2. I turn that on. What do you notice that happened? Okay, well, if I touch this point here, we can see that that's at 0 and 2. So we definitely can see that our y-intercept has changed, right, from where we were before. What about our maximums? Well, we can see that at pi by 2, for both of these, that has changed too. Before I was at 1, now I was at 3. So it appears that my whole graph, my original graph, my parent graph, y equals sine x, has moved up, right? It has moved up. Let's take a look at what happens when we turn on the third graph here. I'll turn this one off and turn on y equals sine of x minus 4. I can't even see that one. So why would that be? Well, maybe because my graph only goes down to negative 2. So if sine of x plus 2 moved my graph up to a y-intercept of 2 and shifted everything up, as well as my maximum value from 1 to 3, so that went up 2 as well, maybe this is down at negative 4. Oh, and there it is, okay? So it appears as if our d value is affecting our vertical shift, right? It's moving my graph up or down according to whatever that d value is. And there it is at negative 4, and my maximum value is at negative 3. So not only are we shifting our y-intercept, our max, which means our min will also shift, right? That also means my median line has shifted as well. All right, so that would mean, if we are right about this, that y equals sine of x plus 5.5 will move my graph up to a y-intercept of 5.5. So I just turn this off and turn this on. I shouldn't see it because that's not within my window. So if I scroll back, there it is at 5.5. So we were right about that too. So the amplitude hasn't changed. That is exactly the same. It's as if we lifted our graph up and placed it in this new position. Okay, so let's turn all of these on and change my window so I can see them all. There they are. Okay, so there's all of our graphs, our maxes, our minimums, if we want to show those for all of these, and how our graphs have changed and shifted up and down according to that d value. So it appears that a positive d value will shift our graph up, and a negative d value will shift our graph down. Okay, so go ahead and graph that in your notes, and then we'll summarize our findings. All right, so that's in our notes labeled, and it says, what effect does d have on the graph? And that's actually already written in there for us. It says, the graphs were all shifted up or down by d units. If d is positive, the graph shifts up. If d is negative, the graph shifts down. This is called the vertical shift. So where are we going next, right? We know what A, B, C, and D mean. We have all of the values and we know what they mean. So now, if we go back to our first page here, and just scroll back, where we first started our notes, we've got our two formulas, or two sinusoidal equations. One, y equals a sine b x minus c plus d, and then our cosine one, y equals a cos b x minus c plus d. So now that we know that a is our amplitude, and if it's negative, it flips our graph over, we know that b is what's going to compress or stretch our graph, c is our phase change, or our horizontal shift left to right, and then d is our vertical shift where we're moving ourselves up and down. We're not going to just be changing one parameter. We're going to be changing multiple parameters. Now that you know what each one does, the next part of this lesson, part 2, is going to be seeing how these all work together. For first of all, if we look at the graph and then determine what A, B, C, and D is, or if we're given some information, how can we draw the graph, changing those parameters around. Thanks for joining me today.